Hello everyone, I'm Xinyu Hu from University of Central Florida. In the next 15 minutes, I'm going to present my paper evaluating interaction cue purpose timing for learning and retaining virtual reality training. Interaction cues inform users about potential actions to take. In this paper, we present a study that evaluates the effects of interaction cue purpose and timing on performance while learning and retaining tasks with a virtual reality training application. Our results indicate that participants retain manipulation tasks significantly better than travel or selection tasks. Our results also indicate that immediate interaction cues afforded significantly faster learning and better retention than delayed interaction cues. Previous works have identified 7 cue purposes: discover, look, go, pick, manipulate, gesture, and speak. In our study, we investigated go, pick, and manipulate cues, which we will refer to as travel, selection, and manipulation to match common VR terminology. In general, most interaction cues are immediately presented. In our study, we also investigated the effects of interaction cue timing at 3 conditions: 0, 8, and 16 seconds delay. The reason we choose these conditions is that attention spans have been reported to be as little as 8 seconds and 16 seconds as double of 8. We used a pre-designed VR application for this study. This slide shows the example of the cues in our study. Travel cues to provide navigational assistance. Selection cues inform the user to select a particular object or element. Manipulate cues inform the users to move an object to a new position. The learning session lasted approximately 60 minutes. After informed consent, each participant would be randomly assigned to one of the 3 timing conditions. The learning session began with a background survey and a STEAM VR tutorial. Participants will then interact with the virtual operating room team to troubleshoot the surgical robot after an instrument failure. To accomplish the scenario, the application requires the user to complete a variety of steps, including travel tasks via real walking, selection tasks via virtual hands, and manipulation tasks via virtual hands, such as stowing a robotic arm. The scenario involves a total of 24 steps, including 4 travel tasks, 13 selection tasks, and 7 manipulation tasks. After the training, participants were required to finish a knowledge test and some user experience questionnaires. The retention session occurred 1 week later and lasted approximately 30 minutes. The participant would experience the same VR training application without interaction cues. After successfully completing the application, the participant would be given a free response exit survey and compensated $15.
Now that the wrench has been inserted, you need to turn it a quarter turn counterclockwise.
They've turned the wrench a quarter turn counterclockwise to open the grips.
As we can see from the video, the interaction cue will show up immediately after the audio instruction in 0-second condition, and there is an 8-second delay in 8-second condition, 16-second delay in 16-second condition. Our independent variables were the study session, learning or retention, the purpose of the interaction cues, which are travel, selection, and manipulation, and the timing of the interaction cues at 0, 8, or 16 seconds. Our dependent variables were automatically collected by the VR training applications for each step. Our first dependent variable was the mean time to complete each step. Our second dependent variable was the mean errors committed while completing each step, and they were grouped according to task type. Our final dependent variable was the mean task success of completing each step without any errors and before a 30-second timeout. The timing of the interaction cues was controlled between subjects, with 3 cohorts, 1 for each timing condition. The session varied within subject, as every participant experienced both learning and retention session. The purpose of the interaction cues also varied within subject, as the application involved all three types of tasks. For each metric, we conducted a three-way mixed repeated measures analysis of variance at 95% confidence level. The Chaparral wheel test of normality was used to ensure results were approximately normally distributed. Degrees of freedom were corrected using greenhouse gaser estimates of sphericity when Moseley's test of sphericity indicated that the assumption of sphericity had been violated. Bonferroni corrections and post hoc tests were used to correct for type 1 errors in the repeated measures and to identify significantly different conditions when a significant main effect was found. We found a significant two-way interactions between the session and purpose. Post hoc tests indicated that the learning task times were significantly faster than the retention task times for all three purposes. In the learning session, the travel task times were significantly faster than the selection and manipulation times. In the retention session, the manipulation task times were significantly slower than the travel and selection times. We found a significant main effect of purpose. Post hoc tests indicated that selection times increased significantly less from learning to retention than manipulation times, and there was a statistical trend that selection times increased less than travel times. We found a significant main effect for timing. Post hoc tests indicated that the 0-second timing condition was significantly faster than the 8-second condition overall. We found a significant two-way interaction between the session and purpose. Post hoc tests indicated that significantly more errors occurred during the retention session than learning session for all three purposes. In the learning session, there were significantly fewer travel errors than selection errors and manipulation errors. And there were significantly fewer selection errors than manipulation errors. In the retention session, there were also significantly fewer travel errors than selection errors and manipulation errors. And again, there were significantly fewer selection errors than manipulation errors. We found a significant two-way interaction between the session and purpose. Post hoc tests indicated that significantly more learning tasks were successfully completed than retention tasks for all three purposes. In the learning session, significantly more travel tasks were successfully completed than selection or manipulation tasks, and significantly more selection tasks were successfully completed than manipulation tasks. In the retention session, significantly more travel tasks were successfully completed than selection and manipulation tasks. We found a significant main effect of purpose. Post hoc tests indicated that the decrease in manipulation task success was significantly less than the decreases in travel and selection task success. We found a significant two-way interaction between the session and manipulation tasks. Post hoc tests indicated several pairs of significantly different tasks and interactions. The post hoc test indicated that task 15 was retained significantly better than task 14. Task 14 is removing the faulted instrument, and task 15 is handing it to one of the virtual agents. Task 21 was retained significantly better than task 20. Task 20 is collapsing the robotic arm, and task 21 is stowing it away. A similar interaction effect can be seen between tasks 10 and 11, which both involve using the same tool. We found a significant main effect for timing. Post hoc tests indicated that the 0-second timing condition was significantly better than the 8-second and 16-second conditions. Our results indicate that for our VR training application, travel tasks were easier to complete than selection tasks, which were easier to complete than manipulation tasks. It could be the reason of the different precision and degrees of freedom. Our travel tasks were low precision 2 degree of freedom tasks, requiring the user to move to approximate positions within the horizontal plane. Our selection tasks were low precision 4 degree of freedom tasks, requiring the user to select one option from a set of options. Most of our manipulation tasks were high-precision, 6-degree of freedom tasks, requiring the user to position and orient an object within a confined volume. Hence, the travel tasks were clearly less complex. Another reason might be the egocentric travel tasks were easier to complete than the exocentric selection and manipulation tasks. Another potential explanation is the fact that the 2D icons travel cues used in this study were easier to understand than the semi-transparent 3D objects for selection manipulation cues. Our results indicate that participants retained manipulation tasks better than travel or selection tasks. One potential explanation for the better retention of manipulation tasks is that participants leveraged an object-oriented form of context-dependent memory. Based on our results, for each manipulation target, the initial manipulation task was less successful than subsequent manipulation tasks involving the same target. We believe the target of a manipulation task can serve as the memory context. Once a participant starts manipulating a target, the same memory region and subnetwork of neurons will be activated, making it easier to recall and execute subsequent manipulations involving the same target. Since many VR training applications combine travel, selection, and manipulation tasks, the ratio of these three types of tasks may have an impact on the overall effectiveness of each application. Our results suggest that manipulation-heavy training applications such as surgical simulators may yield better retention than selection-heavy training applications such as assembly-based applications. Our results indicate that the 0-second cue timing condition afforded significantly faster learning and better retention than the delayed conditions. Instead of having participants demonstrate their retention through a declarative knowledge test in our previous study, we had participants to demonstrate their procedural knowledge by executing the same tasks that they performed during the learning. We believe the results of this study are a truer indication of the effects of interaction cue timing. Among the data we collected, we also found an interesting result. Although participants in 16-second condition committed more errors, their mean test time is faster than 8-second condition group. Based on our observation, instead of waiting 16 seconds for a cue, participants in 16-second condition attempting to accomplish the task before the cue show up. This finding recommends that developers should generally avoid delayed interaction cues and focus on providing interaction cues as soon as they are relevant. There are limitations to the generalizability of our results. As mentioned previously, we used a specific previously developed application for this study, with only 4 travel tasks, 13 selection tasks, and 7 manipulation tasks. However, it is still a good starting point for research into the effects of interaction cues. There are only 60 participants successfully finished both sessions, and only 11 females included. Peck et al. Have recently found that changes in simulator sickness in VR studies are associated with the proportion of female participants. If simulator sickness systematically varies with the proportion of female participants, it is possible that learning and retaining VR training do as well. For future work, we plan to begin controlled, systematic investigations of interaction cue purpose. We specifically plan to study how the required precision and degree of freedom of a task affects the effectiveness of its corresponding interaction cue and the retention of the task itself. In conclusion, based on our study results, travel tasks are easier and immediate cues are more effective. Thanks for watching my presentation.